Good morning, everyone. This will be your Exam 4 Solutions video. It's Saturday morning, and before I go out and mow that Serengeti of a back lawn I decided to go ahead and record the exam solutions video for you, so that you could have ample time to study for the final exam. Uh, just to remind you, the final exam is this Thursday, and you cannot drop it, and it's worth 25% of your grade. So make sure you take that final exam. Same rules apply for all exams, and it will include information all the way from the very beginning of the semester and end with the last two chapters that we do on Monday and Tuesday, which are the synthesis chapter and the alcohol chapter. And for you go-getters out there, I've already posted the notes for those lectures. The lecture videos won't be posted until Monday and Tuesday as normal, and the assignments and quizzes. But at least the notes are there, so you can get a head start for you go-getters out there that want to see it ahead of time. So let's go ahead and get started with this exam video, so I can get out there and mow my back lawn that looks like the Serengeti. Let me change the view real quick. There we go. This is exam 4. Okay, exam 4. First question. Which of the following carbocations are likely to undergo a rearrangement through a hydride shift? Well, we've got a secondary carbocation there, we've got a secondary carbocation there, and then we have a tertiary carbocation there. This guy definitely will not go through a hydride shift. It's already happy, being its tertiary carbocation itself. So the only two answers left are these two here, 1 and 3. So the answer is E. Next, identify the major product of the following reaction. So when we have this here, this basically means hydronium and water. That basically means it's an acid in there, right? And so this is actually an acid catalyzed. That's an acid catalyzed hydration. And if you recall that in a acid catalyzed hydration, these do Markovnikov addition of an OH. Right? And what that means is what? It gets substituted at the most substituted carbon, right? Or it gets added at the most substituted carbon. Well, can't be structure V, or 5 rather, because there's no OH there at all, okay? Can't be structure 1 because that's not even where the double bond is, okay? Again, can't be structure 4, not 4, which one am I at here? Oh yeah, okay, so it can't be structure 4, because that's not Markovnikov addition, right? You're stuck with these here, right? And, actually can't be this one here, because that's not where the double bond is either. So there it goes. Structure 3 is the answer. Okay? Or structure III, as I say. Next one. What are the optimal conditions to achieve the following synthesis, right? This is another acid catalyzed hydration. Okay, and the key to this one here was figuring out whether or not it was going to do the acid catalyzed hydration, or if it was going to do a dehydration, right? And so, since you're actually going this way, and you're adding an alcohol, it's going to require some dilute sulfuric acid. So the answer there is C. None of these would have been right at all, right here. But if you were to use concentrated sulfuric acid, it would have reversed the reaction and dehydrated it, right? So the answer here is C, right? So that's another acid catalyzed hydration. Oh my gosh, I didn't know it could do that. I've been trying to use the scroll bar this whole time, and I didn't realize I could just hit the next button and it would go on to the next page of the PDF. That's crazy. Okay, so What is the expected major product of the following reaction? So this is, if you recall, an oxymercuration, right? Demercuration reaction. Okay. Again, this is going to do a Markov addition. Right. And the point of doing an oxymercuration demercuration is because when you do not a Markov addition, but a hydration like you did in the acid catalyzed, you can't control whether or not the carbocation rearranges. Okay, but since you have the mercury here, it makes that cool little mercurium ion, right? Yeah, am I saying that right? I always get that wrong. I always say it wrong. I might have just said it right for the very first time ever in life. Mercurium. Anyway, the point is, excuse me, the answer will be answer 2, right? Because you are definitely adding on an OH right here, right? And there's no OH there, okay? And then this would actually be this would be wrong too, and that would be wrong too. So, and then also when you're doing a hydration of this type, you only get one hydration. It's just picking whether or not it's Markov or anti-Markov. And since we know that the oxymercuration doesn't do any kind of rearrangement, we're going to get this one. Right? We're going to get that one. The Markov addition. Okay? Yeah, this one was the anti-Markov, so that's why you can't do that one. All right. Oh, maybe, no, let's going to move to the next page. I don't want to move to the next page. I want to just go down. Okay. Which of the following will accomplish the synthesis right here, right? So this reaction here is, it's not super obvious, but if you recall, there's a syn addition right here, right? Of a hydrogen and an OH, right? So water, basically. And so you got to draw that in there, right? This used to not be there before. And so this is actually a hydroboration oxidation reaction. And if you do a hydroboration oxidation reaction, what do you have to have? You got to have boron. So that's A. I always call it boron trihydride, but everybody else calls it borane. Whenever I say boron trihydride, at least I can recall what the structure is, you know. Okay, next one is identify the expected major identify the expected major organic product from the reaction below, right? So we have here a alkene with a boron and a water. That's going to be the halohydrin formation. And so in the halohydrin formation, right, we do the OH addition, of course, again at the Markov site, at the Mark site, right? And then we do the bromine at the anti-Mark site. Or in other words, we add the OH at the more substituted site, or we do the bromine at the less substituted site. Right? So can't be that one because you got to add an OH and a bromine. Can't be that one because you're still missing an OH there. Okay. Can't be this one because you're missing a bromine there, so it's between these two. Okay. And then you're going to be adding the OH at the more substituted one for Markov addition. So that's right there. And then the anti-Markov, which is less substituted, is right there. So the answer is B. Next, Which of the following intermediate is formed when 4-methylcyclohexene reacts with Br2 dissolved in CHC? Yeah. See, it's uh, carbon tetrachloride is what that is. Okay. So this is actually pretty easy because you remember that boron is one of those that doesn't go through a carbocation intermediate, right? It's got that weird thing where it can attack from both sides of the the thing. And so, since it's boron, we get that what is it called again? Bromonium ion, I believe. Bromonium. There we go, bromonium ion. All right. And since we get a bromonium ion, this is obviously a bromination halogenation reaction. Bromination halogenation. Dog just woke up. Sorry about that. It's always Kobo. He's always the one that's moving around. So yeah, since it's that reaction, it's not consistent with a carbocation intermediate. Okay. This is not even an intermediate, so it can't be that one. This is not a radical reaction, so it can't be that one. And it's a bromination / halogenation, so it doesn't go through a carbocation intermediate. It goes through the bromonium ion, right? So it can't be either one of those. The only one that's a bromonium ion is that one. So the answer is B. Okay. This one should be pretty easy because it's asking the major organic product for this reaction, which we have osmonium tetrachloride. Excuse me. Osmonium oxide there, tetraoxide, right? And so this is simply an addition, a syn addition. Right? Syn addition dihydroxylation. Right? So you're adding OHs at the syn positions, syn to each other, right? None of those are actually stereochemically defined, right, or configuration defined. Here the OH is on the other is pointing out at you, and the H is pointing inwards. Here the methyl group is there, syn with the OH, so that's wrong. So the answer is B again. Okay. Next, we have ozonolysis. Okay. Good old ozonolysis. And in ozonolysis, literally, remember what I said in lecture, you cut the molecule down the center of the double bond, right? And then those double bonds become carbonyls, like that. So now those molecules are literally the same molecule, just flipped upside down from each other, right? So what matches this? So let me draw this out so it looks like you can see it a little bit better. Right? So that's what it looks like. Not this one, right? Because we have an extra carbon there. Not this one because that's not even, I don't even know what the hell that is. Where that came from. Not this one because it's got to be a ketone, not an aldehyde. Okay? And then not that one because that has some extra stuff on it that I don't know where it came from. So it's actually going to be this one. And it's actually two of these right here. Right? Because it's split right down the middle. So the answer is C. Good old ozonolysis, right? I'm a big fan of ozonolysis, so you make sure you study that kind of stuff. Okay? Alright, next thing we have here is we have a what is the major expected product for this reaction sequence? First thing to notice is that the first thing you're adding is a tert butoxide, right? Tert butoxide is a bulky base. And then whenever you use a bulky base, right, to make a double bond, right, to do an elimination and get a double bond, what do you get? You get the Hoffman product, right? So quite simply, we're going to get rid of the chlorine through elimination and get a double bond down here. So after you get the Hoffman product, right, and the double bond is down here, this is a potassium permanganate with sodium hydroxide and cold. So what that is that's going to be a dihydroxy hydroxylation again. Dihydroxylation. There we go. Xylation again. Right? So this was actually 2 steps. Okay. The first step was the elimination using terpbutoxide, giving you the Hoffman product right there. Okay. Remember, if it were like something else that was thinner, more slender based, like just sodium hydroxide or something like that, or methoxide, then it would have been a slender base that would have given you the Zitzev product. But this is the Hoffman product, right? If I can spell Hoffman, how do you spell Hoffman? Oh, you get the point. Hoffman product, right? And so that's why the double bond is down here now and not right here, right? During the elimination. And then after your elimination happened, you have the potassium permanganate there, which means that's a syn dihydroxylation using potassium permanganate. And so the only one here that has, let's see here, the only one here that even looks like that is this one right here. Okay. So, because we're not going to get this, we're not going to get double bonds there, or a carbonyl, it's not ozonolysis, right? You're definitely getting a dihydroxylation, so it's not that one. This one's at the wrong carbon, and you're not getting carbon dioxide and carboxylic acid, so it's definitely this one right here. And I know that this doesn't look like a syn dihydroxylation, but it's a good way to think of it. But just recall that this is a single bond that can rotate, and then that OH will be at the right position, right? So really, it's just a dihydroxylation. But remember, though, it's usually a syn dihydroxylation with a potassium permanganate. All right, rank the following hydrocarbons in decreasing order of acidity. Well, we know that the alkyne is more acidic, and we know that the alkane is less acidic. So the only one that has 1, 2, and 3 in that order is D. Oh, sorry, most acidic to least acidic. So 3, 2, 1, C. That's the answer there. Oh, here I go with the 2-step things again, right? So we're going to begin with a bromine, right? So that's definitely a halogenation reaction. Right, where we have that brominium ion again. And that's going to be an anti-addition, which actually ends up not even mattering, right? But it's going to be anti-addition of the bromine. Okay. No more double bond. Okay. So then you add in 3 equivalents of the sodium amide in ammonia and water, and that's actually formation of an alkyne. With elimination. Right? So the sodium amide, so there's a proton there, of course, and then there's a proton up here, of course, right? And the sodium amide will come over. Oops, not that. Not 2 ends in a row, that's weird. There we go. Sodium amide will come over, pull off this proton, form this double bond here, kicking off that guy, right? Kicking off that Lubin group, and then the sodium amide will come over here. I did it again with 2 N's, I meant 2 H's. Come over here, pull off that proton. That comes out, form a double bond there, and then this bromine leaves, and so you'll get this product here. And the name of this product is, got a methyl on the 3 there, right? Get the alkyne on the first carbon, so it's going to be 3-methyl 1 hexyne. So that's going to be E, right? All right, the next question, number 13. Select the major product for the organic product. Select the major organic product for the reaction below. We have a sodium and ammonia here, so this is going to be the dissolving. Oops, not the buzzolving. The dissolving metal reduction reaction, right? And so this is going to be stereoselective for an anti-addition. Of the OH. Not the OH, sorry, of the H. Right? Of the hydrogen atom. And so, in this case, if it's anti-addition, right, that means it's going to be trans. The only one that's got trans at the right double bond here, right, is number 2. Okay? That's... that's not, there's not even a double bond there. That's at the wrong carbon. That's at the wrong carbon. And this one's actually cis, right, or syn addition. Okay? Next, we have Lindlar's catalyst and some hydrogen gas. And so this is going to be hydrogenation. Right? Hydrogenation. But it's going to be a partial reduction because we're using the poison catalyst, Lindlar catalyst, right? If it were just hydrogen gas and platinum or something like that, or palladium by itself, then it would be a full hydrogenation. But since it's poisoned with Lindlar's here, it's only going to be a partial hydrogenation, right? Or so in other words, only one of the pi bonds are going to get reduced. And then also, this will be, instead of, unlike the previous one, unlike the previous question, this one will be syn addition. Not anti-addition, right? And the product of the product of a syn addition will be a cis alkene. And so the answer there is 1, right? Because that's the only one that's got cis right there. Right? It's cis at the right carbon. That's a trans. There's not even a double bond there. That's at the wrong carbon. And that's at the wrong carbon. So that's A. Next, what is the final product of this reaction? So this is a hydration, mercuration, right? Hydration with a mercuration. Mercuration, right? And so in this reaction, we end up with a carbonyl. Well, actually, we end up with an enolate first, right? An OH. Let me just write that, erase that real quick, and do that again. We end up with an OH, right, to a double bond, like that, right, and a little like OH, and then it tautomerizes to the carbonyl, right, and tautomerizes to the carbonyl. So, since we know that it tautomerizes to the carbonyl, we know it can't be any of these because you don't stay with an OH, right? It tautomerizes, and then this is only going to be a single hydration with the OH there, right, in the hydrogen atom, not a double, so it can't be that one. So the answer here is structure 3, which is C. Okay. Next, we have our excess bromine and carbon tetrachloride again. So this is the halogen. I was thinking about that Beyonce song Halo. That's probably why I said halo. Halogenation, right, of an alkyne. Okay, and when you have excess Br, you get what we call tetrahalides produced. Right, there, that's what's produced. That's only a dihalide That's only a dihalide. That's only dihalide. That's only the only tetrahalide we have here is structure 5, or V. Next, rank the following radicals in order of decreasing, excuse me, decreasing stability from the most stable to the least stable. Okay, so this is pretty easy to find the first two, the first and last anyway. This one's going to be the least right here because it's a primary. Okay, this is going to be the most because it's a tertiary. Just like carbocations, radicals are the same way, right? So it's between these two, which is going to go first and second, or sorry, first and third. First and third? No, second and third in this list, because both of those are secondaries, right? The difference, though, is that this secondary is all the way up here by itself, but this one here can do resonance, right? And give you this structure. Okay? And so since this is a secondary that's resonance stabilized, that would be the second one, and then this will be the third one. The regular secondary will be third. So it should be structure 4, and then 2, 3, and then 1. So, oh, sorry, I said that wrong. Should be structure 3, and then 2, and then 1, and then 4, right? So that would be answer E. Okay. Next, what term best describes this process shown here? We have a radical, so it's going to come over here to the secondary position and abstract a proton. Let me just do that again. I didn't draw that very well. Undo, undo, undo. We have protons here. And this radical is going to come over and abstract this secondary proton. Not that far. Like this. Right? And then this bond will come down here like this. Or not bond, but that one electron that's still there will come down like that. Okay? And so, I didn't even draw that correctly. Let me do that. So it's so important to draw this correctly. I'm not even drawing it correctly for you. It's just so small is the problem. There we go. And there we go. So that leaves us with that there. So what happened there was a hydrogen abstraction. Answer C. Definitely not a proton transfer because you'd have a charged species if there was at the end if there was a proton transfer, right? Next, which of the following represents an example of termination? Well, that's pretty simple because a termination means you don't have any more radicals left. The only one that has no radicals left is what? Is this Br right here, this bromine compound, right? 2-bromopropane. So that's structure or reaction 3. So that's C. Okay. Next, which option shows the result of a feasible addition of radical to a pi bond, right? If you recall, when you're working with radicals, you always have to have 3 arrows, and those 3 arrows have to be single barbed arrows or fishhook arrows, right? That's only 2 arrows, so that's wrong. And the reason why that's wrong is because it didn't show an arrow for a radical coming back to the carbocation right here, right? I don't know what the heck is happening there. That's just, I don't know. That's wrong. I don't know what's happening there either. I don't know what's happening there either. So the only one that's left that is even remotely right, which is actually correct, is structure 4, which is IV. Or D, rather. Okay, next one. What reagent would best accomplish the following synthesis? Well, we have here the allylic addition, right? Or allylic halogenation of bromine. And the only thing that we know of that can do an allylic halogenation of bromine right? Or addition, sorry, allylic addition of bromine to the alkene, to an alkene. I put all those words all together. My bad, right? The product here is an allylic bromine, right? Bromine, bromine. Yeah, okay, bromine. And the only thing that can do that, right, do this kind of halogenation, allylic halogenation, is NBS and heat. Okay. Next, which of the following shows the correct products that are initially formed when ozone interacts with light, UV light? I don't know why there's a chloride there because I don't have any CFCs flying around at the moment, so that's wrong. Shouldn't be any charged species, and yeah, it shouldn't be any charged species. Okay, you should have, well, what you should have left over is an oxygen molecule, right, and then a single oxygen atom, right. And so when you have a single oxygen atom, right, you already know what what a Lewis structure looks like for a regular O2 atom, right? But when you have a single oxygen atom, I might as well just draw it for you. The molecular oxygen O2 atom, O2 molecule looks like this, right? And it has 2 lone pairs. And then the atom, the one single atom of oxygen, right, is just an oxygen, right? And it actually has 6 electrons on it. The answer here would be A. It's the only one that's right. Okay. There's the correct Lewis structure for an O2, and there's the correct Lewis structure for an oxygen atom, a neutral oxygen atom. So it's A. Next, identify the intermediate that leads to the major product in the reaction of 2-methyl-2-butene with hydrogen bromide and hydrogen peroxide, right? So we have a couple things to notice here, right? This is going to be a radical addition. Radical addition, right, of bromine, okay, or of HBr rather, not just bromine. And then we have here hydrogen peroxide, and that always gives us an anti-Markovnikov. Markovnikov? No. Anti-Mark addition. Okay. So let's just take a look at what the actual structure is for the starting material here. It's going to be something that looks like this, like that. I have it drawn backwards, but you get the idea, right? So what's the point is, though, what's going to happen is that the since it's anti-Markovnikov, right? Let me just make this a little bit thicker. Since it's anti-Markovnikov, right? The bromine will end up over here, and then a radical will end up over here because of the anti-Markovnikov addition. And so the only one that shows that is this structure 2. I have it drawn backwards, but you get the idea. Okay. Here we have an actual polymerization reaction, right? Using using a peroxide, and so the peroxide being the initiator, what the initiator is going to be, it's going to be a peroxide radical, and then it will initiate a reaction, right? A radical reaction like that. And then it will give you another radical over here that you can use to attach yourself to another. I drew it upside down. Undo. Undo, undo. Attach yourself to another one of these benzene monomers. Right? And then this one can do the same thing again and attach itself to another benzene monomer. So quite literally, you are propagating this radical reaction until it terminates. So the repeating species is going to be one that looks like this, right? But with a single bond, right? Because you lost your single bond when you attached over here with a radical, and you lost you lost your double bond when you attached over here with a radical, and then you also lost your double bond when you attached on this side with a radical, right? Double bond, okay? When you attach on that side of the radical. So the only one that matches that is this one. I have no idea why any of these would be correct because none of those, right, have the benzene ring just hanging, right? There's no reason why this benzene ring would end up in the chain. It's just hanging there like as a side chain. So the only one, I don't know why I cross it out because the answer actually is this one. So let me just do that again. There we go. I don't know why it would be this one or this one or this one because the benzene ring is literally a side chain hanging, right? It's not even it's not even involved in the propagation, right, of the radical reaction. So none of those are correct, right? And this one right here is the only one that matches up with what you get as the chain propagating up there, right? When you lose this double bond, right, through radical propagation and initiation, to make single bonds on that side and single bonds on this side. So yeah, the answer here is definitely 2, or B. And then in our last one, which of the following arrows show termination by coupling of 2, right? So the only one here. So remember, you can't have a radical reaction with double barbed arrows, right? Or normal arrows with 2 barbs on it. They have to have fishhook arrows. So that's not a correct one because that has a double barbed arrow. This one has 2 double barbed arrows, so that's not right either, right? And then this, so it only leaves these 2 here. Okay, it only leaves these two here. But remember, when you're doing a radical reaction, 2 radical electrons must come to join each other, right? They have to come together, right? It's not like when you do it with a pair of electrons. So a single barbed arrow right here is incorrect. So the only one that's got the correct arrows is actually this one. That's structure 3. And so the answer there is 3, right? Or C. And that actually ends the test. So I think this test went actually really well. And there were no grading errors that I saw on the exam. But I still think I'm going to give everybody an 8-point curve on this exam. So yeah, I'll give everybody an 8-point curve on this exam. But just make sure that you get to studying and prepare for the final exam because that's going to be a doozy, right? It's going to have a lot of information on it. It's on Thursday, and it's going to have new information on it too from the synthesis chapter and the alcohols chapter. All right. So good luck on that. I'll be around, and don't forget to do your lab assignments. I mean, I think that people get so caught up in doing their lecture stuff, but don't forget to do your lab assignments too. Okay. All right. I'll see you in the Monday lecture for. I just said what the lecture was about. Synthesis. The synthesis lecture. Okay. Have a good weekend. But you'll probably watch this after the weekend, so I hope you had a good weekend.